Okay, so in question 6 we're starting with Kw, and the first question is simply to define it. So we just get that Kw, remember, is the ionic product of water, so it's just the product of the H plus concentration times the OH minus concentration in an aqueous solution. So that's all you need for the first one. And then in part 2 we've got to use that to calculate the OH minus concentration. So first of all, if the pH is 4.37, then again you've got to remember how to convert that back into the H plus concentration. So H plus is the inverse log of minus the pH, or 10 to the power minus 4.37, which works out as 4.266 times 10 to the minus 5 moles per dm cubed. Okay, so that's the first thing that you've got to make sure you've figured out, is how to get from the pH to the actual H plus concentration. And then we can use that number in here together with the value for Kw at 25 degrees C in order to solve for the OH minus concentration. So from the graph you can see that at 25 degrees C Kw is 1.0 times 10 to the minus 14 moles per dm cubed, which is also the value that you're given in the data sheet if you use that one. And you can see that if we rearrange this expression at the top, we can solve for OH minus simply by moving the H plus over to that side, and as usual it moves diagonally, so we get Kw divided by OH minus, divided by H plus is equal to OH minus, which is what we want to solve for, which is 1.0 times 10 to the minus 14 divided by 4.266 times 10 to the minus 5, which comes to 2.3 times 10 to the minus 10 moles per dm cubed. Okay, so very low concentration of OH minus, which is what you'd expect in an acidic solution at around about pH 4. Okay, now the next part is asking us to look at the graph and use that to tell us what's happening to the equilibrium as the temperature changes, and therefore whether the reaction is endothermic or exothermic. So you can see clearly that Kw increases as the temperature increases, and you should state that because that's simply what the graph is showing you. And then remember that just from the definition of Kw, if its value increases, that means that there's more ionization. In other words, more H plus and OH minus as the temperature increases. Okay, so the equilibrium, which is this, is shifted to the right as you go to higher temperature. On the other hand, Le Chatelier's principle tells you that when you go to higher temperature, the equilibrium will shift in the endothermic direction to oppose the temperature increase. Okay, it shifts in the direction that takes in heat to oppose the temperature increase. So Le Chatelier says that the equilibrium shifts in endothermic direction as the temperature increases. And if you put those two ideas together, you can see that shifting to the right is the endothermic direction. Therefore, the answer is that ionization, which is what the forward reaction is. So when it shifts to the right, it's going in the forward direction, which is ionization, is endothermic. Okay, which is quite a lot of work for 1 mark, and you wouldn't actually have to write all that down to get the 1 mark. But that's the thought process, at least, that you need to go through, and you should write down as much of it as you need to make sure you've got it the right way round. Okay, now we've got to find the pH of pure water at a different temperature at 37 degrees C. So the point is, it's not going to be 7, because the equilibrium constant changes with temperature, as the graph shows you, and as you would expect, we're going to get a different pH. So the first thing you have to do is read off from the graph what the value of Kw is at 37 degrees C. And you can obviously only do that fairly roughly because you haven't got a very accurate scale there, but you get from the graph Kw is, and I read off 2.3 times 10 to the minus 14 moles squared dm to the minus 6 at 37 degrees C. Okay, and you know, they allow you a little bit of leeway on that because the graph isn't very accurate, but do it fairly carefully to read off the number. So then, as always, we think, what do we need to do to go from that value of Kw to the H plus concentration? And remember that in pure water, which is what we've got here, and only in pure water, Kw is equal to H plus squared, because the H plus concentration and OH minus concentration are the same, because every time water ionizes you make one of each. So provided you haven't added anything else to the solution, the two concentrations are the same, so H plus times OH minus is the same as H plus squared, and therefore the H plus concentration is just the square root of that, so it's the square root of Kw. So we can take the square root of that number. Square root of 2.3 times 10 to the minus 14 is 1.51 times 10 to the minus 7 moles per dm cubed. And pH, remember always to write this bit down, because you know it's usually the last stage of these calculations, and often you know, it will get you a mark. So you just get pH is minus log to the base 10 of the H plus concentration, and if you take minus log to the base 10 of that, you should get 6.8 is the answer. Okay, then we get this, one of these sort of just thinking about the consequences questions, and it's only 1 mark, it's only looking for something very simple. So it says that people often use the famous value of Kw, 1 times 10 to the minus 14 mole squared dm to the minus dm squared mole squared dm to the minus 6. They often use that at any old temperature, even though strictly speaking it's only valid at 25 degrees C. And it's saying, what does this matter? So the answer obviously is that, you know, conclusions based on that could be invalid if they apply to other temperatures. But the trick with this question is it's not enough just to say, oh, the conclusions could be wrong or the conclusions could be invalid. You've got to spell it out and explain why. So always with questions like this, state what may seem obvious, because the whole question has been about the fact that Kw changes with temperature, but you've still got to say that. So you say Kw changes with temperature, and therefore conclusions may be invalid if they don't take account of this. And that gets you your 1 mark. On to the next bit. Right, so this is this designing an experiment thing for 6 marks. So this was slightly intimidating because you think, well, how much detail do they want? And the general answer is you don't need lots of practical detail in terms of saying, you know, what size flask you'd use, and or even you know, whether you'd use a burette or a pipette or anything like that to measure it. What they're interested in is the principles of the experiment. You know, what quantities you have to measure, and how you would then process the numbers you measure to calculate the answer. So you've got to use your imagination a little bit and come up with an experiment that would give you a value. And obviously there are lots of possible variants of this, but you've got to come up with one. So don't be too general. because it just says, you know, plan an experiment. So long as it will give you the right number, it doesn't matter if it's slightly different from the one that someone else would come up with. So, what we're looking at is enthalpy change of neutralization. So the first thing is that we've got to identify a neutralization reaction. So choose something simple, and let's say our reaction is going to be sodium hydroxide plus HCl. You know, it's the most obvious neutralization probably. Sodium hydroxide plus HCl goes to the salt, sodium chloride plus water. Okay, and we're going to measure delta H of neutralization. For that, remember, it's defined as the enthalpy change per mole of water formed. But because this is a nice easy reaction, the moles of water formed is the same as the moles of sodium hydroxide and the moles of HCl that react. So what are we going to do? Well, we're going to have to add a known number of moles of that to a known number of moles of that and measure the temperature change. And to do that, what you're going to have to do is to say, well, you know, we're going to do it in solution, so let's choose a volume, choose a concentration, and say that's what we're going to take. Okay, so we'll say take 25.0 cm cubed of 1 mole per dm cubed sodium hydroxide and 25 cm cubed of 1 mole per dm cubed HCl. That would be an example, but obviously you could use different volumes, you could use different concentrations, but you've got to specify what you're going to use. And crucially, we're adding equal numbers of moles so that we'll just not have to worry about excesses and things. Alright, so that's the starting point, and those solutions we have to measure their temperature before the reaction starts, because we're going to measure the temperature change. So measure the initial temperature. And again, not lots of detail, you don't need to go on about, you know, what sort of thermometer you'd use, just say you'd measure the initial temperature. And then you mix the solutions so the reactions can occur, and measure the final temperature, or the maximum temperature reached, because remember it's an exothermic reaction, so measure the maximum temperature after mixing. And then that will give us the temperature change. The difference between those two is delta T, our temperature change. Then you have to remember how the calculation works. So you say that a heat released in the reaction is MC delta T. And you're going to have to explain what those numbers are. So that's equal to the mass of the solution times C, remember, is called the specific heat capacity of the solution, times the temperature change, in other words the difference between those two temperatures. So you've got to spell that out. Don't just write MC delta T without explaining what those quantities are. Okay, so we're going to calculate that, and then remember we've got to change that heat released into heat released per mole of water formed. So the next step is that we've got to divide by the number of moles of water actually formed in the reaction, because we want the heat released per mole. And you can see that we've got moles as concentration times volume for the moles of NaOH, which will be the same as the moles of H2O. So that's equal to concentration times volume in dm cubed, which is 1 times 0.025. In other words, we divide by 0.025 to get the energy change per mole. And now we're almost there, but remember we have to worry about the sign of delta H. This is an exothermic reaction, and so delta H is going to be negative. So we write delta H is equal to minus the energy change per mole that we've just calculated. Okay, so it didn't need a huge amount of experimental detail, but there were a lot of steps in there, so you had to work quite hard for your 6 marks. So look quite carefully at what you came up with and see how many of those steps you got in there, and therefore how many marks you think you would have got. And you know, if it wasn't great, just see step by step that we're taking quite simple ideas. You specify the reaction, you explain how you would set the reaction up, so just come up with some sensible volumes and concentrations. Crucially, explain what you're actually measuring in the experiment, which is the temperature rise. So you measure the temperature of the solutions before you start, and then the final temperature after the reaction. And then take them through the MC delta T calculation, exactly as you would do it. But obviously, because you haven't got numbers, you just have to explain how it works. And remember, don't just bring in C and M and things like that without explaining what they are. Okay, now part D again took a bit of thinking about, and the best way to think about part D is to sketch out the little cycles that we've used for analysing delta H of solution. So if you've revised this stuff, the cycle you could sketch out very quickly, and that would help you think about what was going on. So the idea is that for either our potassium fluoride or our rubidium fluoride, so let's call it M fluoride, MF solid, we're going to go around the cycle and we're going to end up with M plus aqueous and F minus aqueous at the end. And remember that it's just a 2-step cycle basically, that you first of all have to break up the solid and turn it into M plus gas plus F minus gas, and then, well, we normally do this in 2 steps because we hydrate the ions one at a time, but we're just taking the M plus ions and putting them into solution, and then taking the F minus ions and putting them into solution. And these 2 terms, well, this one, that's the reverse of the lattice enthalpy. Okay, lattice enthalpy is the enthalpy change when you take the gaseous ions and bring them together to form a mole of the solid, and you're just doing that in reverse. So that's minus delta H lattice going up there, and coming down here, that's delta H of hydration of F minus plus delta H of hydration for M plus. Okay, the enthalpy change when we take those ions from the gas phase and introduce them into water. So what we're saying is, well, how does this term change when we go from potassium to rubidium, and how does this term change when we go from potassium to rubidium? And what makes it hard is that they both change. So if we focus on this one first of all, remember lattice enthalpy depends on the strength of attraction between the ions. So what you'd say is, remember that K plus is smaller than RB plus. So just a reminder here that you've got to be very careful about that. Don't say potassium is smaller than rubidium, or still worse, a potassium atom is smaller than a rubidium atom. We are talking about ions here, and so you must specify the particle. So K plus is smaller than RB plus, therefore K plus has a higher charge density. Okay, same charge, but packed into a smaller volume. So it has a higher charge density. And the consequence of that, remember, is that K plus is more strongly attracted to F minus. And that in turn means that the lattice enthalpy is more exothermic for KF than rubidium fluoride, than RBF. Okay, but this term is minus the lattice enthalpy. Okay, so that term, so minus delta H lattice, is more positive for KF, more endothermic, more positive for KF than RBF, because we've just changed the sign of the lattice enthalpy. So if it was more negative before, now it'll be more positive for KF than RBF. Okay, so far we've gone further uphill with KF than with RBF, but now we've got to come down this way, and again there's going to be a difference. So for the same reason, again, because K plus has a higher charge density, as we've already said, than Rb plus, so it's more strongly attracted to water molecules. Remember, these ion dipole forces in water depend on how big the charge on the metal ion is, because the bigger that charge, the more strongly it'll be attracted to water, but it also depends on how small the metal ion is, because the more that charge is packed into a small volume, the stronger the attraction. So higher charge density means more strongly attracted to water. Okay, and that means that delta H of hydration is more negative for K plus, or for KF if you like, than for Rb plus. Okay, if it's more strongly attracted to water, then more heat will be given out when you introduce the ions into water. So now you have a problem, because the first term is more positive for the potassium ion than for the rubidium ion, but the second term is more negative for the potassium ion than for the rubidium ion. So the question is, which one of those two things wins? Well, we know the answer, because overall you can see it tells you that delta H, the overall change down here, which is that change, is more negative for rubidium fluoride. And that means that the fact that rubidium fluoride takes you less far up here outweighs the fact that it then brings you less far down this way. Okay, because rubidium fluoride ends up with a more negative change, that must mean that the fact that rubidium has a less positive term there, rubidium ion has a less positive term there, outweighs the fact that it has a less negative enthalpy of hydration. So the final idea is that, therefore, the higher, or the more exothermic, now let's get this clear, it's difficult to put into words, but the more endothermic first term, so the more endothermic minus delta H lattice term, outweighs the more exothermic delta H of hydration term for KF. So overall, KF has a less exothermic enthalpy of a solution. which is what the data tell you. So that really takes quite a lot of getting your head around. But as in lots of these questions, it was relatively straightforward to get some of the marks, even if your brain had burst by the time you got to the end and you didn't quite get those ideas together right. But go through that slowly, see if you can convince yourself that the reason it's complicated is that these two contributions to the solution cycle both depend on the charge density of the ions. And because the potassium ion is smaller and has a higher charge density, that's going to be more positive and that's going to be more negative. And where the overall balance comes in depends on which of those terms is more important. And the fact that overall we end up higher up with a less negative overall change for potassium fluoride tells you that this term predominates over that one. And you just need to take a little bit of time to convince yourself that that's true and see if you can get to the point where you think, if I had a problem like that, I could analyse it at that sort of level. Okay, the final part of that sort of that question is asking something much more predictable, because this is this sort of old chestnut of a question. Essentially, is how are endothermic reactions possible? And this is something you need to have practiced and be able to explain. And it starts from the idea, remember, that in order for a reaction to be feasible, delta G, which is equal to delta H minus T delta S, must be negative for a process to be feasible. That's the key idea. So it doesn't just depend on delta H, it depends on delta S as well. So in this case, we're told that when ammonium nitrate dissolves, delta H is positive. So delta H is positive. So for delta G to be negative, you can see that T delta S must also be positive, and crucially it must be more positive than that one. So when you subtract a big positive number from a smaller positive number, you get a negative answer. Okay, T delta S must also be positive, and specifically T delta S must be greater than delta H. Because if it is, we're taking a small positive number, taking away a bigger positive number, so we end up with a negative answer, which is what we want. And that's really all you need. That delta S must be positive for this solution process, and sufficiently positive that T delta S outweighs the delta H to make delta G negative overall. And that's the end of what was actually quite a challenging question.